Question 3 on the you do.
I did. I was trying to find question.
Okay, so 3, 9.
Oh, man, that's really quick. Are you just coming in today?
Okay, 3, 9, and you want you do.
Yep. The third question.
Question number 3. All right. So they're performing chromatography. They're going to let it sit overnight. They want to determine if the mixture contains an RF factor of 0.343. The RF is calculated by distance traveled to the component divided by distance traveled by the solvent. What data would be affected by the error? If they left that overnight, it's going to run off the paper. And then you can't figure out what your RF value is because it ran out of paper. Okay. So the distance traveled by the solvent, you can't determine that because it's just going to keep going. Yeah. Yep. Yep. So you can't leave those things overnight.
Okay.
Why would it be too high?
The distance traveled would be too high because it's running off.
Yeah, it's going to run off the paper. So it's, yeah, you're not going to be able to
Measure it.
measure
It'll
it.
be
Yeah.
too long, yeah.
Because it would have just kept going off out into here and you don't know how far it would have gone.
Yes.
Wait, so with the solute is what stops, right?
Yes.
So that would just stop, and then the rest of it would run off the paper? Or would it just keep going, but very slowly?
The solvent would probably continue to run.
But the solute would stop.
Mm-hmm.
And because the distance...
And eventually this dot, it would probably, I would guess that the paper would start dripping the solvent onto the floor. Okay. And this line, this dot here would eventually end up running off the paper too.
Eventually, but it would take a while.
Yeah.
So you just can't even solve for the R?
Uh-uh. All right, what else do we want to talk about?
I have a question for question number 10. Can you just explain what it would be?
9, 10. This is your 10? Is this the 10?
Yeah.
Okay. Okay, so
Yeah,
this...
I said A, but because the answer key wasn't on, like, I couldn't find the answer key.
It was on yesterday.
Oh, yeah. I did this, like, what did it, okay, so it says that it's D, right?
It's like the arrow.
I don't get,
Well, I have A circled here.
yeah, I would say A too.
Oh, I said A, but your answer key says
Yeah,
D.
your answer key
And
said
online
D.
it says D.
No, but then in the PDF it says A. It has two different answers.
Like your post-it note thing says D.
Okay, so don't pay attention to the post-it note, I guess.
Yeah. No, but another source that I checked on, because I did this like Thursday when this was set up. The source that I checked online also said D.
I just said D because I have multiple speeds, so you can tell.
Like now I know, but like
You should
before
all
that.
just say
'Cause
that
it's at a-
ideal.
Okay, well, let's...
Which of the diagrams best
I would say A. I would say A.
I said
I'm gonna read it.
A makes more sense
This.
since B has different.
Yeah, I would keep it there because it's at a fixed temperature, so they're all the same. So they should be the same.
Yeah.
Now you've got me going in circles.
Oh, we could have checked on this. Oh,
College
my.
board. Man.
I don't have it. I can't get to it.
D is the answer.
D
have to do it all tonight.
Oh my gosh.
Based on kinetic molecular theory, gas particles have a distribution of speeds that is dependent upon temperature, which is represented in diagram 2.
Okay.
And if you think of like the Maxwell-Boltzmann curve, right? They're going to have variable speeds here. Some of them are going to be going slower than others, but the average speed, which is what your temperature is measuring, is going to be it's an average speed of those particles, but some will be moving slower, some will be moving faster.
Can we go over the Boltzmann?
Maxwell-Boltzmann, that's what this is.
Yeah, I know.
Yeah. Not good.
One more time.
So this gas X here is going to, they're at the same temperature. X is going to be heavier than Z. Yep. So lighter things will have a higher average speed than heavier things. Okay, Ben will run around the track much faster than me because he's lighter than I am.
Actually?
Yeah.
Yes, ma'am.
Oh my gosh, me too.
Did he say 124?
Yeah.
What?
All right. What else do we want to talk about other than my weight?
I'm petite.
You're slender. You're petite.
Petite.
Bella's like, you're petite.
I am petite.
For a 16
Annie, did that answer your question, hon?
Like, no, I know. I got
Okay.
the right answer. I just like wanted like a review on how.
Did I give you a review of it, or do you need more?
It was heavier.
Then it would
It would be like,
It would
no,
be-
it was lighter. It was lighter than it would be.
Lighter will
goes
be
over
there,
here.
So it's hotter temperature.
Yep.
Heavier,
So
closer level temperature.
the higher peak, what are like I can't remember what causes it to peak higher rather than
Well, fewer of, if we had the same amount, right? Fewer of them would be shifted this way. So if we had another, like something that was even lighter, it would peak like here, but it would end up going out further.
So like there's less of gas.
No, it would be the same amount, but it's it's going across the X further because it's going from here all the way to here.
Yeah.
So if you have the same amount, it's going to get squished down for its
So
top.
instead of being like this, it's gonna be like this. But you're still gonna have the same amount.
Yeah, but like what makes the one peak taller than the other? It's more
Higher temperature or lighter molecule.
So lighter also makes it a taller peak.
No, a shorter peak.
Which is kind of crazy because
Okay.
Because the shorter ones are going to go further.
So heavier is just more condensed. So
Mhm.
taller.
Yep. All right. Is that good? Are we done with Maxwell-Boltzmann, or do we need to talk more?
So
Okay.
it has a higher peak if it's a lower temperature and the heavier molecule. It has like less of high temperatures, high speeds, and okay, I get it.
All right. What else we want to talk about? Sir. 26.
good question.
Is this your 26?
Yes.
Okay. All right. So we have our radiation here that's being transmitted. They've given us a wavelength here. This is infrared. So remember, infrared is heat. I don't even know what this is asking about, but when I say infrared and heat, I think of vibration, friction. Is that what the question's asking?
Yes.
No. Oh, vibration. Yep. You're talking about vibration here. Yep. Okay. If it was microwave, that would be rotational.
Yeah.
If it was moving from energy level to energy level, that has to be transitional. And that is light waves and higher for frequency. And then this doesn't make any sense. Did that help? All right, what else? So you don't really even need this graph to help you with this. This graph gives you nothing. Huh? Yep, you need to see infrared. And when you see infrared, you think of vibration. Or sometimes, you can think friction, but yeah, vibrational friction, moving back and forth, vibrating in place.
I was trying to do something and it didn't work.
What other things shall we talk about, my dears?
I was trying to pick up my cat book because no one in the school seems to take it past at night.
What do you have some in the bag?
I don't need
Such a whiner.
If you take the cat. Yes. Take my cat. Why? You seemed to want it yesterday.
No, I'm looking at what were you doing?
Can we talk about the FRQ section?
Yes, sir.
Which one?
The second one.
What part?
For part B, I used the word, there's like an ion dipole interaction between the water and the salt. I don't know if that's the right word to use or not. I'm just wondering.
One more. Next one.
Yeah, so it would be ion dipole. Yep. So the ions of the NaCl are attracted to the polar water molecule.
Because they're polar. Yeah.
All right, what else? I've been everywhere, man. I've been everywhere. Been to the progress check, been to the worksheets, and now I've been to the multiple choice project check, progress check.
The equations, like the light. I remember the equations. No, you don't even.
You don't need it's in your formula sheet. I think it's one of the very first equations on that formula sheet.
Right here. Oh, this is
No.
not ours, but
No.
I don't want to get it out. Maybe.
The higher the
You guys
moon,
have
the
number one.
less
Like I kind of get it.
Number
Oh, what?
1 FRQ,
because it has
multiple choice. Okay.
Did I?
because more of the solution
I got
was,
most of
so
them.
not as much water is put in, so it wasn't as
I don't do it.
Oh, this one. I just remembered
Is this
that
number
one.
1?
Yeah.
Okay. So we're looking at the attraction here between these. Okay. Now, this is a carbon and a hydrogen.
Yeah. So that's
They're being attracted. Is there hydrogen bonding here? No, it's not on the phone. Over here, we've got hydrogen bonding because this is oxygen. This is the hydrogen attached to an oxygen. So the electrons are going to get hogged on this side. This side will be more positive. Here, this side will be more negative. They're going to get attracted to each other. Now, I have not even read the question, but I've gotten that much analyzed. Okay. So now I'm going to go in and look at the question here. Which particle diagram represents the strongest IMFs present here? Well, we would say definitely diagram 2. So now we've got to figure out why. So we've already eliminated it down to these 2. Diagram 2, because the formation of the hydrogen bond, that sounds valid, but we're going to go and read this one real quick just in case, because it shows the dipole from the ethanol inducing a dipole from the ethanol. Induced dipole is what type of, right, and LDF is usually not as strong as,
Unless there's a lot of things.
but
that's not the case.
right, no. So C is definitely your answer there. Did you see how I did that? I didn't even look at the question and I was able to kind of preview what they were going to be asking for just from the diagram.
Yeah.
Multiple choice, I assume.
Yes.
Okay, 10 degrees Celsius, we got 20 grams of oxygen. We got a pressure here. We got a rigid container, assuming ideal behavior. Temperature of the gas was raised to 40. What's that going to be? So we're going to take... Now, this was back in the day when we didn't have calculators on the multiple choice. Okay, so you guys are kind of lucky that way. Yep. All right. Google still has not allowed me to figure out how to write on any of their stuff. So I have to switch over to this guy to be able to do that.
Oh yeah, I just need it.
Okay, here we go. All right, so I've got 10 degrees Celsius. I've got to convert that into Kelvin. So I've done that here. Okay. And then I'm going to have a rigid pressure of 2.1. This value here is not going to change. It's a rigid container. So the 7 liters is going to stay the same. And then I'm going to convert this 40 degrees Celsius into Kelvin. And I want to know what my new pressure is going to be. So you can divide and then multiply by 313, and that should give you 2.3. Now, does it make sense that the pressure increased when we increased the temperature?
Yeah.
Okay, so if that's the case and our pressure was at 2.1, we can get rid of this guy and this guy automatically.
That's what I did. I just
Okay,
didn't do it.
and then you've got to be able to do these 2 math problems.
And the 283 that came from where?
Right here, 10 degrees Celsius.
Oh, okay.
You have to convert it into Kelvin.
Because you always gotta do stuff like
No, I
that.
do that. It's just I do it in like a weird way. I just wanted to know.
Yeah,
Oh, really?
but you can automatically, without doing any math, you can get rid of A and C right away.
And
Well, I said without doing any math because you know that your pressure should increase.
no, yeah, but without math,
You
we
could-
also
you could-
because you need
You could
Kelvin.
probably do it without math, because like you know it's.
Oh,
gonna be
yeah.
bigger.
Yeah,
Right
so
there.
You know
Yep.
it's in Kelvin, so you don't
Yeah.
even need to do math.
Yeah.
Yeah.
That's what I did. I
Yeah,
just
you
got
don't,
A and
yeah,
B
you
and
can't
then
do, you can't have it here. You got to convert it into Kelvin. So this guy is out.
Yeah. Genius. Good job.
See, I told you guys you're smarter than I am.
Oh, you do have rubber gloves in here.
I would hope
Thanks.
so. So that.
All right, what else do we want to talk about?
Um, no.
The total gas thing. So when you have 2 gases under different
Mhm.
pressures and you combine them together, they still experience the pressure that they were experiencing when they were in this previous container, right?
No.
Like, no.
You would add the pressure.
You would add
Yeah.
the pressure, and
Yeah.
that's the total.
The partial
Yes,
pressures.
but then
Those are the partial pressures.
yeah, yeah.
But they're going to have a new pressure because you got a
I know
new
they're gonna-
volume.
I know they're gonna have a new overall pressure, but like the pressure on each individual gas.
Not necessarily, because if your container gets bigger, the pressure will go down.
Everything stays the same. If you were to remove one of them,
The moles stay the same.
Okay.
You're going to have the same amount of moles, but the pressure and volume might vary.
because they're together.
I don't know what question she's in.
I
Nine.
think I saw what you were
I
guess
got
we
it.
talked
I know.
about
I
nine.
get it.
But you just need to know that the sum's equal.
Yeah. The container size is the same.
Now, so, you know
So
the
because
sum
of that,
equal to the
yeah, the
initial.
pressure, you would just add them together.
This is what we're doing.
What is it?
So they're doing
What
something.
about number 2 of multiple choice?
They're doing like E equals
You say number 2,
wavelength
Katarina?
times frequency. Which one?
Yeah, I got that one.
All right. So we got cations are shown at the same scale, which cation would be predicted by Coulomb's law to have the strongest ion dipole attraction to water and why. Okay, so these are smaller, so they're going to have more of an attraction. So we're going to get rid of these right away. Now we've got to figure out between these two which one it's going to be. It's going to be this one because its charge is twice as much as this guy.
So not the bigger ones.
No,
Why is the bigger one bad?
Big bad
because
boy.
your protons that are pulling in are in here, and there's more of a distance there between the protons and the electrons that it's getting attracted to. Increased distance equals decreased
So
force.
if that was like the opposite charge, if it was like, just hypothetically, if calcium was like -2, would that be,
Oh, I was.
would a bigger one be better?
I was. My juice box, probably.
Because it would be further away from the.
Oh,
But it's
yeah,
going to be
I have
attracted to
those.
the opposite side of the water.
I almost hit a car yesterday because of it. I dropped this straw, so I accidentally got off
Okay, smaller is
the
better.
brake, but it didn't happen. It was fine. I didn't really like the dude anyway, so I.
So you were fine with hitting it?
Well, no, but I mean, it was better than someone else.
What if it was
I wasn't going fast enough to do anything, so.
I saw it was just bad driving like this with his juice box.
I'm a little slow driver.
Ben would do that.
All right, what else we want to talk about?
Next one. Hello, being deal
I've
with
asked enough
question.
for this.
I'm looking. 1 second.
Go back to like where I was thinking. 3.10, solubility and precipitation. I did not get how to write those equations at all. I passed the work. It's just like a whole new sheet. I have both in there. Oh, it's not in there.
Lovely.
You can't invest
Like a
in this,
separate
this is
worksheet.
a scam. My favorite hospital in the United States.
You need one of these.
Do you have a favorite hospital?
You're kidding. That's my favorite hospital in the U.S.
Why is it under stress?
Favorite hospital in the US?
Mayo Clinic. It's the best hospital in the U.S.
Oh, what do you mean?
Give me a company, like anything.
Mayo Clinic, say, please.
No, what's our
No. I know.
honestly?
So far down.
It's 0.039.
I have to think about it. Should we really start?
Yeah.
You need one of these.
You still work at Target? Didn't you work at Target? That's Mary.
Yeah, Jordan.
Oh yeah.
Oh, yeah.
Yeah.
You know that's how they met.
Yeah, that's how
They met.
They both worked at Target. That's how they met.
Are you have the last story?
Some Target man. Good for them.
He
What's that?
still works at Target. He
I
just
should
works at
get one of
another
those. I think I deserve
Crazy, you
it.
don't see them anymore.
I don't know if people at Target do that.
Target went up.
Target went up.
Yeah, tell us I'm gonna kick you.
I don't think so.
Okay?
Okay.
Yay, that was good.
And these shoes are like
Actually, with the holidays.
Please.
coming up, I don't know.
Please,
They give me like an inch.
Let me go back.
That hurt my leg.
That one. That one?
Oh,
That is it.
yeah.
You need this thing.
That is utter torture.
What is
Please.
that?
What is
Utter
it?
torture.
Tear.
Tear.
Yeah, it was that.
I have a
I didn't have
suffering.
any answers on it, honey.
Oh.
Trying to look for the answers.
What part of it do you not understand?
Nestle.
You okay,
I
bro?
appreciate your input.
That's why I.
don't wanna eat it.
Ben, can you take your cat back?
No, I don't wanna eat it until.
What are the TVs?
Katerina, what part do you not understand?
The whole thing. I
Look,
put
do
big
you
question
remember
marks in
the
every
sheet you
part.
gave us last year with like the steps to breaking down equations?
I was not in there
with
last
like the
year.
divorce
Well, you still
been
probably
and,
did it.
and that stuff. Maybe that'll help her.
Yeah, well, you said we're doing balancing equations next unit, so we'll just go.
Is that it then? Oh yes, Ben found it.
That's how we do the reaction.
Oh, great. Thanks, Ben.
I know, you're welcome.
And this is how you figure out if it's soluble.
That's terrible. I don't want to see that.
You just like find the thing and like follow it,
That's,
and then it's not.
you could have just sent, can't you see if it's polar?
Okay, so is there something on solubility that you don't understand?
Oh, I got
Solubility
the
and
solubility thing. It's just I was really confused on writing the equations, finding how many waters go to one of them. Well, actually, I know how many.
Will we need to do that in the test then?
You don't need to know how many waters go to it, no.
Oh. I thought you did.
Is there a lot of balancing? You said there's not a lot of balancing.
Not on this
I'm
one.
trying to
Whatever. I got some
balance
sections
I don't
homework done for
like
that. It's just I didn't understand anything on this part, like how to write them. So,
it. What is this for? Oh, I remember that. That's when you have to count the things.
You do have to count the things.
No.
We should get, I don't like these colors though. I
So
don't
here, you're looking at your lead. I've got that here. And see how it says aqueous? That means it's broken up into its ions. Here is your NO3s. Okay. Here is your sodiums and chlorine. And notice how they're not attached, except for the nitrate. They're not attached to one another because they're all aqueous. Okay. When we come over to this side, our lead chloride has produced a precipitate, which means it's formed a solid. So the chlorine, two of the chlorines, the two is there, two of those have gone with one lead, and it's gone down to the bottom. It's sunk down to the bottom. That's your solid precipitate. And then these things are still aqueous, so they're still floating around up in here.
So I won't have to like say, oh, this is solid.
You just need to know the numbers.
The only ones that you need to know that always stay aqueous are, it's a snap. So that is your sodium.
Yes.
So sodium, nitrates, ammonium, and no, potassium.
What is it? What?
And that means that there's
So anytime that those are in a formula, they're always going to be aqueous. So this sodium, that's why it stayed aqueous. This nitrate, it's going to stay aqueous. Yeah.
sodium starts with Na.
It's on the parade.
The solubility,
On like the aqueous.
yeah,
That's the things like floating up here, right?
it's talking about the solubility.
Same side.
What is aqueous?
Aqueous means that it stays dissolved in water. Like aquatic, think aquatic is water. So these are going to stay dissolved in water. Great, you make a better door than a window. Move.
No kidding. You could.
And so S is sodium, N is nitrogen,
No, nitrate.
nitrate.
So sodium, nitrates, ammonium, and potassium.
What is P? Phosphate?
Oh, yeah.
No, not phosphate, potassium. So these two are alkali metals. Okay.
Nitrates.
And then nitrate and ammonium. These are always, no matter what combination they're with, they'll always be aqueous in water.
What's ammonium?
NH3.
No,
No, NH4.
plus one.
Investing.
That's why we say it's a snap.
Even though potassium is a K.
So if there's one of these in there, then the entire.
Sodium.
Then that material is going to be
Oh yeah.
Oh, okay.
soluble.
And ammonia
So here, you started out with lead nitrate, that would be soluble. We started out with sodium chloride, that's soluble. Okay, we had two different containers. Ben, can you sit down and be quiet? We had two different containers, and then when we mixed these together, all four of these things together, this is what resulted. These came together and formed a solid.
In the left half of the equation, why is chlorine aqueous?
Chlorine is commonly aqueous. Occasionally it won't be. So it's not part of the snap because it's not an always situation. But very commonly it is, like salt water. Like you've got an ocean of salt water. You know that's aqueous.
That's true.
Okay.
We do.
How do you know? Because like the lead is also aqueous. How can you tell?
Well, because it was married. So this is what's called an ionic equation. Typically, these are written like this.
NaCl, yeah. I don't like those. NaNO3.
And I got to put a 2 here and a 2 here. Okay. So typically they're written like this, and then you need to know, oh, this is aqueous. I mean, you know this is aqueous. You've got salt water, right? Okay. This you would know is aqueous. How? No, nitrate in it. Okay. So this has nitrate in it. This, you know, is going to be aqueous because it has nitrate in it. And then if you had a precipitate, they would say a precipitate forms. You would need to know that this is what your precipitate is then. And you can do that by a process of elimination because you know that this is aqueous.
Is a precipitate, what's the abbreviation for that?
It's either an S like this, or sometimes you will see PPT.
PPT Lex.
Yes, S is solid. A precipitate.
You can just label it as solid.
Yeah. Yeah, because that's what it is. That's what a precipitate is. I don't know if you've seen.
I don't even know what that means.
You don't know what a precipitate is? Okay, give me just a second to find a precipitate for you here.
A precipitate
Isn't
usually.
it like solid and liquid? Like, it's like solid and liquid.
Like precipitation.
The solid that forms it.
Are we even gonna
So
need
here-
that much tomorrow though?
This isn't a bad review for you guys. And if you have other questions, I'll answer them next. Okay, so here they're adding, hush, hush. Here they've got a clear liquid here, okay? And they're going to add in, watch when they drop this liquid in, okay? And this dropper here, watch, that's going to be clear until it hits, okay? So see how it's clear when it's dripping out of that dropper? Okay, so you got two clear soluble liquids. Now it hits there, it forms this stuff. This is a solid. If you let this sit overnight, it'll end up coming down into the bottom of the test tube. So it settles down to the bottom.
We should do that. I should do that for my project.
So like that.
Yeah, I guess.
Oh.
Okay.
What's your project?
So like this is what would happen if we
After the
just
test,
had
yeah,
a
like,
board because there's
one
a
of those
solid
ones.
in it.
Yep, it'll form a solid. When those two clear liquids mix, it forms that solid. So this was soluble. Whatever was in here was soluble. But when they end up mixing here, it forms a solid. And in the equation, oops, that's the wrong one. Hold on. In the equation, that's what they're showing you here. Okay, let's say that was the two clear liquids in there. The one was in the dropper and this was in the test tube. When they met, then this solid, that yellow solid, formed and settled to the bottom, and then the rest of this stuff was left up there to float around.
So for it to be aqueous, does it need to be paired with one of the snaps?
Not necessarily. But,
Is there a way to tell?
well, they're typically your heavier metals and polyatomic ions, those typically will end up forming precipitates. But you don't have to have any of those memorized. They're not going to have you in situations where you wouldn't have something that's obvious here. You need to know the snaps.
Snaps are always aqueous.
Yep.
You said,
Always.
but they don't usually be part of something. Or for that something to be aqueous. I said that weird. Something doesn't need to include anything.
Right. It could still be aqueous. Yeah.
I confused.
All right. What else do you guys want to talk about? So paper chromatography takes place on paper. I'm not being sassy. Okay. I'm just saying. And then the other one, the thin layer chromatography. Sometimes it's on paper, but it always has a silica gel or silica component to it, okay, because that silica or alumina is very polar. Okay, so it makes the paper or whatever medium it's on really, really polar. Sometimes it's on a thin thing of plastic, sometimes it's on glass. But yep. And it's very polar.
So when would you use thin layer over paper with one of the other?
A lot of times the thin layer is used in organic chem for like these enzymes. They talk about the enzymes here. And a lot of times it's used for that.
Did you use both of them in a similar situation?
It says here that the thin layer one is typically used with samples that don't have color involved.
Thin layers when you use one that. Okay. I've heard so much about it. What is this for? It's like the weight. How many questions are on the system?
What?
How many questions?
Same as always. So 30 multiple choice and then like 4 or 5 FRQs. All right. Anything else? Good?